Hello, everyone. This is Dr. Tina Burns. Welcome back to the Summer 2025 section for Computer Architecture. I'm your host for this evening or morning, and this is Lecture 3C, which is for the third week and the third lecture of this particular module. So let's go ahead and get started. Today, we're going to talk about assembly language processes. We'll go through some information on registers, and then we'll also look at some sample assembly code. So, I like to think about assembly language kind of in steps. It helps us to understanding a little bit better. And we can think about assembly code and kind of the instructions being written in three categories. Your action processes, which help you perform data manipulation, like, do I want to add, subtract, or compare two data items, or other processes like that. The memory process. So what do I need to do to access and manipulate information in the memories or registers? That includes loading, storing, moving, and also just basically determining what memory address it's at. And then finally, we have our control processes. Our control processes allow us to alter the flow of the program. What does that mean? So typically you have your program running from um, A to B or one to two in sequential order, but your control process will allow you to supersede that order in order to jump to another portion of that program. So let's look at kind of how some of these commands look practically. When we think about action processes or data manipulation, we're thinking about things that involve two operands or that involve two items or more, and you want to perform a specific task on them. You want to take the data that you have and you want to do something with it. It could be addition, subtraction. It could be some sort of comparison algorithm. But you're basically um, taking data and you want to manipulate it somehow. Now, here are some of our action processes and kind of what they look like in assembly code, right? So your column here on your left is going to be the instruction, and that includes um the column here on the left is the instruction, such as add or subtract, multiply, dividing, increment, decrement, and your bitwise operations such as and, or, and not. Now, when we look at these things like the add operation, for example, we have some samples here shown on the side for this assembly code. Now, if you guys remember from the last lecture and the last conversation that we had in class, when I do an add command, although the instruction involves several processes, when I look at it in the x86 architecture or when I look at it in the sys computer architecture, it's just one instruction, but that involves several commands. So although this one line just said add AX via X, what's actually happening is that it's storing something into that excuse me, it's getting information from both of these registers and then it is adding them and then storing that added value into this register A of X. Right, so that's three different processes that are handled in this one command. Now, if we were to switch that and swap that to a RISC structure, it would have a lot more commands because for each item that it has to do something with a memory or a register, that's going to be one command, and then your operation will be another command. So keep in mind that for RISC, right, you have we have one operation per clock cycle. For this, which is based on the sys architecture, it's doing multiple processes under one one operation. All right. And it's the same story for um the subtraction example here. Now, another thing you'll notice is kind of the flow of how these control processes are going to work. Here on your left side is typically going to be the instruction or action you want to perform. This second item here, or really what's that first item after your value, that's going to be your destination, right? So I want to subtract 5 from A of X, or it's going to be 5 minus A of X, and then you're going to store that value into A of X. So it should be 5 minus A of X, and whatever that value is, it's going to be stored into A of X. This will multiply two values, and all the other ones are pretty much self-explanatory in terms of their operation. Let's look at those control processes. So these are what I'm calling the action processes, which deal with data manipulation. Now let's look at the control processes. Your control processes, again, can be broken down into a few different branches, right? Your control statements include conditional statements, right? And your conditional statements are, of course, things that we are super familiar with and we use a lot of when we program. Your if statements, nested ifs, and your switch. So that tells us if a certain condition is met, then you're going to do something, right? Um, those are all those are all conditional statements. Your iteration statements are anything that deals with a loop. So your while, your for, your do while, all those are going to be your iterations. That means you're going to perform this loop or this set of operations more than once. And then we have our jump statements. Our jump statements for our C code in particular are like whether or not you want to break or continue a program. Break meaning to stop it and not finish the rest of it, right? That's why we kind of call it a jump, or even the actual jump. I don't know why I didn't just put that there. I can update it for that. Another statement is literally jump, right? Go to another portion of the program. And also, if you want to just continue. So actually, give me a minute. I think I'm going to actually add that here. All right, so for our jump statements, these are things that are going to go to a completely different section of the program. We have our break, continue, and or our actual jump. All right, so as we look at these, let's take a look at kind of what some of the assembly language for this looks like. So this is a jump label. Now, we saw this in the last class. Your label is going to be a symbol that dictates a certain section in a program. So it could be the beginning of a function, right? Beginning of a for loop, or beginning of a loop overall. And if you say jump here, then it's going to go to that particular label in a program. For example, if I'm in my main sequence and I have something that says calculate grades, and I say jump calculate grades, that means that it's going to go to wherever that calculate grades function is. And then we have additional jump statements here. Jump if equal to 0, not equal to 0, etc. Going all the way down the line. Your return is a jump because it goes away from your natural program. And then anything that calls a subroutine. And these are kind of like different ways to control or to change or alter the control flow of a program. Now let's look at some of the memory processes. Now for the memory processes, I really grouped them into uh, both for register and memory. And the reason that I decided to do it that way is because a lot of the times they're used interchangeably. Like I might be moving something from a memory location to a register or vice versa, loading something from a registry into memory or gaining access to that. So I kind of group them all under kind of this memory or storage process here, right? When we look at our memory process, they include things like moving information, pushing information, popping information, exchanging it, loading it, storing it, etc., etc. So, some of the things you want to note here um, is, as I was stating before, when we look at these data operations, we want to know the direction in which this particular um, item is being moved. All right, so when we look at this operation, your move function, this second statement or the register right after the instruction is your destination address. This is going to be your source. So what this is going to do is it's going to move B of X into the register A of X. For this is going to push whatever was previously there into the register A of X. Or it's going to push the data onto the stack. When I have this information, this is going to load. That's what this LEA means. It's going to load the lower address of this variable or this variable into the lower address of B of X. And this is going to clear your memory location. All right. So that's kind of just what those two things are doing. All right. So that gives us a little bit of an idea of the flow. Now, let's look at these a little bit more into detail in terms of what they're doing. There's something called load versus store. Now, they really deal with things in terms of register. This gets into the difference between registers and memories. I'm sorry, memory addresses. So for a load operation, that is typically going to be you may be loading something from a CPU register. You could also be loading it from memory. You can do it from either. When you store something, you're typically going to store, like you can load something into a CPU register, but you're typically going to store something in your memory. And your load is typically used for like processes and operations, whereas your store command is going to be more towards like, okay, data storage and manipulation. These are going to be, in terms of the length of time, the storage for the load operation, when you're pulling that data in, it's typically for a short amount of time. You just need it to complete a process and then you give it back. When you store it, if I store something into memory, that means it's going to be there for a while, right? That item, that variable has taken off its jacket and it's going to stay a while. So just keep that in mind that typically when you're loading something into CPU register, it's just to take care of a process and then you want to reopen that register for something else. So now we're dealing with the x86-64 architecture. This architecture has 32 bits. And when you're dealing with the 32-bit version of this, you'll notice that it's denoted with the prefix E. So when you have a register by size of 32 bits, You're going to look at that with a prefix E. Um, you have the option to extend that with accumulation register so that you can get up to 48 bits. And then also, um, when we saw those memory addresses or those lower registers A of X and B of X, they are uh, those lower bits are typically going to be what are used for your lower registers, right? So hopefully that makes a little bit more sense. Now let's look at the x64 architecture. The x64 architecture is larger in size and has 64 bits of information. Now, these are typically going to be denoted with your prefix R, and it has the additional registers 8 to 15. Notice that if I wanted to expand the previous architecture, I can do that with an accumulator register. For this one, this includes like additional registers at the end. And of course, because it's a larger size, you can store more data. All right, so let's look at kind of some of these general purpose registers here. Remember I said so the slash really denotes 64-bit versus 36-bit. But if you notice the end of those and the items and the end of those numbers are actually lower, right? We have our accumulator register, the base register, counter register, right? Um, they're going to be the same. What's going to change is that beginning, which is the prefix. And just remember that your prefix is going to denote the size of the register. All right, so typically if you see these A of X's, you're performing some sort of arithmetic or you're returning a value. When you deal with B, that's your base register, which you can use for just general purposes, is really helpful for manipulating and dealing with data. And also when you start looking into and getting into pointers and buffers and other things like that. Um, your counter registers, um, will help you if you want to do actions and operations with loops. Uh, and then our data registers. So the R, the A, X, B, X, DX are the ones we will see in almost every program, because these are data registers and they deal with the D of X, of course, is going to be a data register is dealing with operations and arithmetic. So we're pretty familiar with those. Now, your RSI is going to be your source register versus your destination register. So where are you taking information from? That's your source register. And where are you storing the information or where's the information going to? Wherever it's going to is going to be your destination register. All right. So let's kind of take a look at some of these in action and look at how it is. If you wanted to look at it in a little bit more detail, when you have these, you can also have extensions to your current register. Um, and you can have additional things like if you're looking at stack management. So since we're talking about registers, let's go ahead and look at those in more detail. Remember I said your A of X and B of X is typically going to be your lower registers. A of X is anytime you want to return a value, you've performed some sort of operation. I want to return that. You can do that in the A of X. Your other ones here where we have they're kind of in this purple. These are more like your arguments, right? A, B, C, D, X, Y, Z, all of those that are being used and manipulated in order to get a particular value. So that's what we have there. And then these are temporary registers at the end that you can use if necessary, right? So this is a good way to look at kind of this Linux usage. Oh, I do want to make a note that the book that we use for this class, right, uh is this programmer's perspective. is from Carnegie Mellon, and these slides are from one of the classes that are taught there. So you'll see them noted with that information on the bottom here, and also a big thing in yellow indicating that that's where these slides came from. Just because they were already put together so well, I decided to include them in my project. So I'm really, really grateful to Dr. Bryant and O'Hill-Larone. Hope I'm saying that right. All right, so that is for your Linux registers, right? Now, let's look at what the standard order for assembly language is. Your RDI is kind of looking at like your first statement. Your RSI can be your second argument. Oh, RDI, I'm sorry, it's first argument. RSI is going to be your second argument. And then RDX will be the result or input, the result or output. So that's one way to look at it in terms of us when we're looking at a particular order. Now, when we look at the commands, there's also something we might see that has like this Q at the beginning and L and all of that. Your Q is just noting that it's going to be dealing with 64 bits of space, while the L indicates that it's dealing with 32 bits of space. So if I had something like this move Q, it's going to move the data into 64 bits of the register, where move L would only move data into 32 bits of the register, and then it's going to fill the rest of them with zeros. All right, so now let's go ahead and look at some of these commands we have here. This LEA is going to be used to compute this value, right? I'm loading this into, keep in mind that these are my two values here, and I'm doing something. I have RDI, RSI, and then I have RD of X, right? Keep in mind that when I have this here, I'm talking about these being my destinations kind of to where this is going. Now, for this particular operation, notice how we have two operands here. So what it's going to do is this actually going to add these two, right? It's going to compute this value. So it's adding this to RDI, RSI, and it's actually going to store it into RDX, right? So it's going to add these two, and then it's going to store them here. So a little bit different than our other one. These are jump statements, jump if greater than or equal to. If that's the case, then you're going to jump to this particular label. And that's how these commands are looking. So let's kind of look up let's look up a conditional move example, all right? What if I have this statement here where I have my I want to find the absolute value of a number, or I'm sorry, I want to find the absolute difference of a number, meaning I don't want any negative values. If I wanted to do that, I can represent that kind of here in this program that we see here. Um, I have two long numbers, x and y, and I want to say if x is greater than y, the result is I'm basically going to subtract y from x. If x is less than y, then I want to subtract x from y, right? And this will enable me to kind of get this positive result that I'm looking for. So here's what it looks like in assembly code. First, let's figure out what we want to have for our registers. We'll have two. We'll have what we're returning, and we'll have our two arguments, x and y. RDI is going to be our first argument of x, our SI is going to be our second argument of y. And we're taking that and we're going to go ahead and get that returned into our A of x. So let's see if we can kind of write this out, right? Let's see how well we do with constructing this. The first thing I want to do is I want to store this here, right? So I'm going to use my move command. And what I want to do is I want to store RDI into a register. I'm going to make that register RA of X. So this right here is going to be my first argument. Um, and then if I wanted to, I could essentially move into my second register. I'm thinking RDX. I can go ahead and store RSI if I wanted to do that. All right. So I moved X into a register, this RA of X. Now what happens if I want to add it, right? I want to subtract it. That's going to be one command that says, hey, let's subtract X from Y. I've stored Y in here now. So I have something for my X, I have something for my Y. And let's figure out how we can store those values. All right, I want to cheat a little bit. Ooh. And we'll see that's kind of what's going on here. My first statement is taking this, it's storing this, it's taking this information and it's storing that into these registers here. Move this into RA of X, move this into you're going to subtract these two, and then you're going to move RSI into this register, and so on and so forth. All right. Sorry about that, guys. So here are two operations. When you think about this, the result X minus Y. Look at how this is being handled. Your RDY, we already said this is X. This is Y. What it's going to do is it's going to take, this is my destination. This is my destination, which is this left-hand operand right here. It's going to take whatever is here, this Y, subtract it from here, and then store it in my destination address. Next, what we're going to do is we're going to move this into our D of X. And now I'm going to take, it's going to be the same thing. My operation is going to say, hey, subtract this from our D of X and go ahead and store whatever the value is here. So this is how I get those values. And then finally, what I want to do is I want to compare X, or actually I want to compare Y to X. That's this line of code here is comparing Y and X. And after it does this comparison, you're going to say if these are less than and equal or equal to. So in other words, and keep in mind that when I look at these equations here, my left-hand side is always going to be the furthest one out. So this goes to this. And then my right-hand side is going to be the one that is further out. This is one that's going to be closest to your expression, and then the other one's going to be in the other direction. All right, so RDI, if X, you can compare them. X, you're comparing X and Y. So If then my register, if whatever is in this destination register, RA of X, if that is less than this, less than or equal to. So right now, keep in mind that my RA of X has the value of, excuse me, my RD of X has the value of Y, or the value subtracted. Okay, so we have here is I'm comparing X and Y. We already know that from the beginning of this statement, X is stored into RD of I, Y is stored into RS of I. So all I'm doing is I'm comparing these values. I know that RD of X, which was the first calculation that I did, RA of X is going to be X minus Y. And then RD of X is going to be Y minus X. All right, so this is just telling me, this is just setting me up for my calculations. So they're telling me basically I'm comparing X to Y. Now, if my comparison says that this is less than or equal to, right? If this result is less than or equal to, meaning if Y is less than or equal to X, then I'm going to use the result versus the evaluation. So the result is this, right? X minus Y. And the eval is the second one. So I choose which one I want to use based on this comparison that happens above. So once we compare these two numbers, keep in mind that the normal return value would be this result up here, RA of X. However, it's basically saying that I'm going to compare these two numbers, and if X is less than or equal to Y, I'm going to move the value of D of X into RA of X, which means I'm going to move this into this position, this return value, and then I'm going to return that instead. So remember I said that R of A of X is the one that is usually returned. So normally I would return this value. Typically that's going to be my standard return. However, if there's a difference, meaning if I compare these values, if I compare X and Y, and I get to a position where Y is either greater than or equal to X, or X is, I should say, really X is less than or equal to Y, then I am going to replace or move the value that I had here into my return register, and I'm going to return that instead. So that's pretty much the program in a nutshell.